Okay, hello everyone. My name is Lucy Fagan, and I was supervised by Dr. Karsten Heger and Reina Mariyama. And I'm going to be presenting on designing the muon veto prototype for the Cupid experiment. Now, just a quick note, I'm going to be presenting on the designing of these panels, and shortly after, Pablo will be presenting on the construction and the testing. However, we both worked on both parts of the process equally over the summer. This is just how we divided the presentations up. So let's get started. I will first give a little bit of the physics background, and then I'll talk about the Cori and Cupid experiments, and then I'll get into the actual designing of our panels. So first, we need to understand a little bit about the neutrino. We know they have mass from neutrino oscillations, but we are still unsure of the hierarchy. We have the normal and inverted hierarchy, which just means we have 2 light and 1 heavy, or 2 heavy and 1 light of the ordering of the neutrinos. We also know that neutrinos have a lepton number of +1 and antineutrinos have -1. Neutrinos are used in a beta decay reaction. So a normal beta decay, we have a neutron that decays into a proton, and it releases an electron and an antineutrino. Then we have double beta decay, which is where a beta decay happens simultaneously in the same nucleus at the same time. And what we're interested in is something called neutrinoless double beta decay. And this is a theoretical decay, which is where double beta decay happens, but the 2 antineutrinos are never actually produced. And this is a violation of lepton number conservation. And so you might be wondering why we care about this decay. It has lots of different implications. The first one being it would prove that the neutrino is a Majorana particle, so it would be its own antiparticle. Next, it would tell us about the neutrino mass hierarchy, like I showed before. It would give us better insight into the inverted and normal hierarchy. Ben explained this a little bit earlier, but we'd be able to either confirm or eliminate, hopefully, the different orderings. And lastly, the lepton number violation would give us better insight into the matter-antimatter asymmetry that we see in the universe. Getting into our experiment, the original experiment is called CORE. It stands for the Cryogenic Underground Observatory for Rare Events, and it's located in Gran Sasso, Italy, underneath a mountain. You can see in the top, there we go. In the top right, we have our cryostat, which is cooled to around 10 millikelvin, which, fun fact, I'm pretty sure it's the coldest cubic meter in the world. And then you can see we also have our tellurium crystals, and the detector is made up of cryogenic bolometers. So we have our tellurium crystal, and it acts as both the source for the decay and the energy absorber, and it has a thermistor on top to make a heat measurement. One of the biggest issues with Core is the background. So a decay is identified by a little energy peak you would see in the energy spectrum at a specific Q value. And so you can see Core has a specific region of interest, but there's a whole bunch of background that's interfering. So all of the green is alpha particles, and then you can see in red, we also have a lot of muons that are interfering with our signal. And so the solution to this is the upgrade called Cupid. Cupid stands for the Core upgrade with particle identification, and it uses slightly different molybdenum crystals and also upgraded light detectors, which are the little wafers you see on the right-hand image, to then look at the heat and light signatures in coincidence and eliminate the particles that we don't want. So, for example, in the center plot, you can see that the alpha particles have a very different light to heat signal than some of the beta and gamma events. So we can look at those and eliminate them from our data. And then here's just a picture of what Cupid will look like. Part of the issue with this design is that this map does not eliminate muons. And so that's where we come in. And we are designing muon veto panels to help eliminate the muon backgrounds in the Cupid inquiry experiments. It comprises of an octagon-shaped setup where we will place scintillating panels around the experiment. And the reason why this setup works is because a neutrinoless double beta decay event will deposit all of its energy into one crystal. And so there's no coincidence, which means it happens just in one crystal. Muons will go through just about anything. It goes through the entire mountain, it goes through the metal, it goes through our experiment. And so the way we can detect a muon is we can see it goes through multiple panels, and that's called a coincidence. And we can identify these and eliminate them from the data. So that was our job this summer, was to build a prototype of a muon veto panel. So we designed this in CAD, and we have our panel with our fibers that we glued into our panel. And then we created some aluminum housing to protect the panel. Then we have a little electronics box over at the end to hold all the electronics, and a removable plate to hold all the fibers together and connect it to the cup. Looking at the housing, we created U-channels for the sides, so that way we can eventually connect all of the panels together and put it into Cupid. We lined the inside with black foam for light tightness, and we put 44 little screws. We screwed them all in to our aluminum housing. Thank you, Donatella, for the help. Looking at the electronics cup, this part was probably the most challenging to model. We modeled it in CAD, and it's a lot tinier than you would think. So it has tiny little springs and screws, and we have our fiber bundle that collects all of our fibers and glues it into place. Then we have our silicon photomultiplier and printed circuit board and a plate to hold it. Then we have our aluminum cup that holds everything together, and then a little Derlin cap at the end to seal it for light tightness. Looking closer at the silicon photomultiplier, or SIPM, and PCB, this is where it converts the light from our fibers into an electronic signal that we can read out on our oscilloscope. So modeling all of this took a long time. We modeled it with CAD and 3D, and we also did mechanical drawings. And the mechanical drawings we then sent down to Craig and Dylan, and they were actually able to use these drawings and help us build a lot of our parts. We learned about tolerances and different types of screws, and so it was definitely a great learning experience. And then we also decided to 3D print our design to see if everything fit together. A model of it right here. And this was actually really useful. We can see some of the fibers coming into it, into our bundle. And then we have a model of all of our electronics, and then the cup that holds it all together. So this is a life-size version of it. And it was really useful to be able to assemble it, and we ended up changing it a lot after we printed it, about 13 times actually. And then just for fun, we printed a little muon veto panel to kind of visualize the spacing and just to have. And then lastly, just this week, we actually were able to build our panel and set it all up. So we built all of the electronics, the cup and the housing. We built our fiber template to measure the fibers and glue it together. And then in the bottom right here, you can see we used a UV light to look at the fibers, make sure nothing was broken. You can see Donatella is very happy right here, and me too. And then here's a picture we took at the end where we put our panel into our efficiency testing stand. It's all encased in the aluminum, and here's our data acquisition setup. And so Pablo will be speaking a lot about the manufacturing and the testing of the panel. So thank you. Oh. And then I'd like to give a big thank you to Donatella. She was with us every day, teaching us about everything, working with us. Also, Zach, Karsten, and Raina for being great mentors, and my mentor back at Cal Poly, who's on the Zoom, Dr. Gutierrez, and the Core and Cupid collaborations, the NSF foundations who is letting me be here, and the Wright Lab and Yale in general. I've had an amazing experience here and have met so many amazing people. So just thank you to everyone. And thank you to James for helping us with everything too. So yeah, thank you. Yeah. It's actually a really good question. So the springs right here essentially are PCB board and SIPM are really, really delicate, and they need to be perfectly aligned with the fibers that come out. So the fibers actually touch the SIPM, and they're coupled together with optical grease. And it's really hard to get that perfect alignment without like in the perfect pressure. And so essentially, I can use the laser pointer. This plate is an aluminum plate and it's stuck in place with these screws to this removable plate. And so this is the PCB and it's fitted to this plate with springs. So that way, if something were to push on it, it would push in. And so we're able to tighten these screws down in order to fit it perfectly to align with our fibers. Yeah, so back to this picture, I would say it really depends on how it comes in. So a muon can come in from all different angles. So sometimes we'll have a muon come in just at the top and it would only hit the top of these panels. Sometimes we would go through the entire thing. And so that's kind of why we've enclosed the entire experiment and the bottom panels too, so we can get it from all angles. And Pablo will speak on this a little bit in his presentation, but we are able to test our panel and with a setup of 3 panels, and you can see that the muon with the right angle will go through all of them.